Hi everyone. Today we are going to talk about how we could classify the Markov chains. Okay. So a state of Markov chain is recurrent if given that the Markov chain starts a certain state I, and the probability that it will eventually returns to itself is going to be 1. Okay? And of course the state which is not recurrent is said to be transient. Okay? So a state I is transient if there is a way to leave the state I and never returns to state I. Okay? So simply what about this? Let's say this is state I, and then say state J. And then of course this state I is transient, right? So there is a way to leave the state I but never come back, right? So obviously state I is transient. Now what about this? How about, let's say this is 99 and this is 01. This I is transient state, right? Right. Although the chances are very small, there is a possibility, in this case, only 1% of chance that you leave state I, but still you never come back, right? So state I is still a transient state, okay? But what if I have this? Let's say this is 1. Is that I is transient or recurrent? Is recurrent, right? Same. J is also recurrent, right? Leave state J, always you can come back, right? It's the same. Leave state I but come back. Leave state I and then come back always, right? So in that case, both I and J's are recurrent, but if I remove this, then I is transient for sure, right? Okay. And state J is reachable. State I, from state I, if there is a path from I to J, okay? And state I and J's are said to be communicate each other. If J is reachable from I, and also I is reachable from J, okay? And I put some extra additional mark here. So it does say if state I is recurrent and state I and J communicate, then state J is also recurrent. Of course, two states that communicate are said to be in the same class. Okay? Okay, now let's talk about the concept of periodic and aperiodic. Like I said, a state I is periodic with period D, and D must be greater than 1. If D is the smallest number, such that all paths leading from state I back to state I have a length that is a multiple of D. Okay? A little bit complicated. Actually, it's not. So, if states I and J communicate, then both states I and J have same period. Okay? And the Markov chain with period 1 for all states is called a periodic. So if a current so if a recurrent state is not periodic, then it is referred to as a periodic, right? So a state with period 1 is said to be a periodic. Okay, then what about this? What is the period of states 1 and 2 here? States 1 and 2 here communicate, right? So both states 1 and 2 should have same period. Is that right? And keep in mind that period of state I is the smallest number, such that all the paths leading from state I back to state I have a length that is multiple of d. I'm sorry. So in this case, periods should be 2, right? So once every 2 transitions, it can come back, right? Every time you leave, it takes 2 transitions coming back, right? Same. Starting from state number 2, take 1, 2, 1, 2, right? Once every 2 transitions, it can come back. How about this then? Once every 3 transitions, it comes back, right? So starting from 1, 1, 2, 3 transitions are required, right? So in that case, the period should be 3. Keep in mind that period of any state is the smallest number of transitions required to leave that state and then returns to itself. So the key word here is the smallest, okay? How about this in this case? What is the period? So starting from 1, there is 1 transitions, probably 2, 3, 4. So is that 4? What about this? 1, 2, 3, 4, 5, 6, 7, and 8. What is the smallest number that you leave the state and coming back? It's 2. 1 and 2, right? So starting from 1, 1 and 2. All right? Same. Starting from 2, 1, 2. Or 1, 2. Same. From 3, 1, 2. Right? So here, the period has to be 2. Because we are looking for the smallest number of transitions required to leave the state and then returns to itself. Okay? Simple concept. Okay, then how about the period of state 1 and 2 here? Because states 1 and 2 communicate. In this case, both states 1 and 2 should have the same period. Is that going to be 1 or 2 then? Of course, with the previous definition right here, you cannot answer this question, right? So I provide you more accurate way to identify the period of state. So like it says, the period D sub I of state I is the greatest common divisor. Okay? The greatest common divisor of all the integer values n, which is greater than or equal to 1. That satisfies this constraint. Okay? So let's look at this. So I'm going to make the transition matrix based on this transition diagram. Okay? So it's going to be P is equal to 0.5, 0.5, 1, 0. Okay? That is based on this transition diagram. Okay? Now we need to check this. So actually we just need to look at the diagonal elements. Okay? Because both subscript is equal. Right? That means we need to look at the diagonal elements of this matrix. Okay? So we need to make a judgment here. If P11 is greater than 0, P22 is greater than 0. Obviously this is correct, but this is not. Is that right? So we can say that n cannot be equal to 1. Okay? Now we're going to have P square matrix. In that case, that's going to be 0.75, 0.25, 0.5, and 0.5. Okay? Again, you need to look at diagonal elements. So you're going to have 1, 1, P22, whether they are all greater than 0. Of course, we are looking at P square matrix, right? So we're going to put P square. Since both satisfies, we can say that n is equal to 2. Okay? So you just need to keep going. P cube, 0.625, 0.375, and then 0.75, 0.25. Again, you need to look at diagonal elements. If they are strictly positive or not. Okay? Since they are strictly positive, you can say that n is equal to 3. Okay? So you just need to keep going. P to the 4th power matrix, that's going to be 0.656, 0.344, 0.688, 0.312. Obviously, diagonal elements are strictly positive again, right? So n can be 4 as well. So you just need to continue on that. So in summary, we can say that n is equal to 2, 3, 4, and so on. Okay? Then what is the greatest common divisor of this number? It's 1, right? 1 is the greatest common divisor of these numbers. So I'd say that the period of these two states, 1 and 2, are equal to 1. Okay? The period has to be equal to 1. Okay? Then what about this previous case? Can you do this? So we're going to have 3 by 3 matrix based on this transition diagram. So we're going to have P will be 0, 1, 0, 0.5, 0, 0.5, and then 0, 1, 0. Okay? So we need to look at diagonal elements. Since all of these diagonal elements are equal to 0, I'm sorry. So n cannot be equal to 1, right? P square matrix, we have 0.5, 0, 0.5, 0, 1, 0, 0.5, 0, 0.5. In this case, all of the diagonal elements are strictly positive. So n is equal to 2. P to the third power matrix is going back to P matrix, one-step transition probability matrix, which means n is not equal to 3. P to the fourth power matrix is same as P square matrix, which means n is equal to 4. So if you keep going that, then you're going to see that the value of n can be 2, 4, 6, 8, 10, and so on. Okay? So in this case, what is the greatest common divisor of this number? It's 2. So right? So that's why the period of these states, 1, 2, 3s, becomes 2. Make sense? Okay? Okay, now let's move on to another concept. Closed set and the minimal closed set. Okay? So like it says in the screen, a set of states is closed if no state not in the set is reachable from a state in the set. Which means once we enter a closed set, we can never, ever leave the closed set. Keep in mind that. Okay? And a minimal closed set is a closed set which has no closed proper subsets. So let's consider this small example. Okay? So what do we have as a closed set here? One, two, three is closed set, right? So if you have here, once you enter this closed set, which is 1, 2, 3, you can never, ever leave this set. Is that right? How about this then? This is going to be another closed set, right? 7. What other closed set do we have? What about 6, 7? That's going to be another closed set. Is that right? What other closed set do we have? Hmm? 4, 5, 6?
Yeah.
But you still can live from 4 to 3 or 6 to 7. It cannot be the closed set. What about this? Including most of states, but 5. This is another closed set. Is that right? So I say 1, 2, 3, 4, 6, 7. Is that right? We do have one more closed set. What is that? Including everything. Right? So 1, 2, 3, 4, 5, 6, 7. Make sense? And among them, both 1, 2, 3, and 7 are the minimal closed set. Is that right? Why? For example, this closed set 6, 7 includes another closed set, which is 7. Is that right? And what about this? 1, 2, 3, 4, 6, 7 does include another closed set, 1, 2, 3, and 7, right? However, both of these closed sets, 1, 2, 3, and 7, does not include any other closed set. Is that right? So that's why we have 2 minimal closed sets for this transition diagram. Make sense? Okay? Okay, so a minimal closed set is said to be irreducible. And Markov chain is called irreducible if the set of states is a minimal closed set. Therefore, a Markov chain is irreducible if and only if every pair of its states communicate. Now let's talk about the concept of absorbing. A state which forms a closed state, that is, which cannot reach another state, is said to be absorbing. In other words, whenever we enter an absorbing state, we can never ever leave that state. Okay? So if state J is absorbing, then this condition is always satisfied. Because once we enter the absorbing state, which is a closed state, right? We can never, ever leave that absorbing state. Does that make sense? Okay? Okay, and Markov chain with finitely many states, a member of a minimal closed set is recurrent, and other states are transient. So let's take the same example here. Let's find out what do we have for transient state and recurrent state and absorbing state. So which states are transient? Which states are transient? You remember a state, let's say state I is transient, if there is any possibility that you leave the state I but never returns. Okay? So if you consider state number 4, there is a way you leave the state but you never come back, right? It's the same. 5, leave but never come back. What about 6? You leave but never come back. Okay? So we have 3 transient states. They are 4, 5, and 6. So even if I put additional transition from 6 to 4, so it looks like in this case 4 and 6 are recurrent, looks like, right? If they take this path, then they can come back always. The same, right? Starting from 6, they can always come back. But the point is, there is another way. You leave the state 6, but never come back. Same. If you take this route, then you will never come back. Okay? So 4, 5, and 6 are transient state. Okay? What about other state then? How about 1, 2, 3? Starting from 1, they can come back always, right? The same. Starting from 2, or it comes back. Same for state number 3. Obviously, 1, 2, 3 is a recurrent state. What about number 7? You leave the state, it always comes back. Okay? Actually, in that case, you can never ever leave that state number 7. Okay? So number 7 should be absorbing and recurrent. Okay? In that case. Any questions? Okay. So now I got to tell you that many interesting applications of Markov chain involves chains in which some of the states are absorbing and the rest are transient state. Such a Markov chain is called the absorbing Markov chain. Okay? And the absorbing Markov chain is not regular. Earlier this semester, we talked about the concepts of regular. Do you remember this? One of the many applications of Markov chain is in finding the long-run behavior, long-range predictions, in other words. Okay? And it is not possible to make long-range predictions with all of transition matrices. But for a large set of transition matrices, long-range predictions are possible. Okay? However, such predictions are always possible with regular transition matrices. And that is the definition of regular transition matrix. So if some power of a transition matrix contains all positive entries, the transition matrix is said to be regular. And a Markov chain is a regular Markov chain if its transition matrix is regular. Do you remember this? Right? And the concept of regular is very important, because we know that if a Markov chain is regular, then there exist limiting probabilities that the process will be in certain state J after a very, very large number of transitions. And this value is always independent of the initial state. Okay? Do you remember this, right? The steady state probabilities, pi j, or limiting probabilities, pi j, that doesn't include the initial state, I, right? Which means these limiting probabilities are always independent of the initial state. Okay? However, the absorbing Markov chain is not regular. So in this case, the limiting distribution for an absorbing chain typically depends on the initial state of the process. Okay? I'm going to show you this later today. So actually, for the absorbing Markov chain, we cannot use this system of linear equations to determine the long-run behavior of absorbing Markov chain. Okay? Keep in mind that we cannot use this system of linear equations for the absorbing Markov chain. Okay? To determine the long-run behavior of the absorbing Markov chain, okay, you cannot use this. And I got to tell you that regardless of the type of Markov chain, for example, regular Markov chain or absorbing Markov chain, we can continue to apply the matrix analysis discussed earlier. So you still can use these Chapman-Kolmogorov equations to obtain the nth power transition matrix. And these computations reveal the probabilistic future of the chain. Okay? So these equations are valid even for the absorbing Markov chain. So in our example, we can obtain the steady state probabilities using the Chapman-Kolmogorov equations. So we can obtain the p-square matrix, p cubed, p to the 4th power matrix, and so on, based on this one-step transition probability matrix. Okay? So if you keep going, you still can get p to the 5th power matrix and then 10th power matrix, like this. And p to the 20th power matrix, p to the 99th power matrix. That is like this. Okay? So, for any absorbing chain, if we begin in a transient state, so which of these 4 states are transient state? Transient state. Right. Transient states are only 1 and 2. Is that right? Because there is a way you leave the state, never come back. You leave the state, never come back. Is that right? So 1 and 2 are the transient state. 1 and 2 are transient state. Okay? So if we begin in a transient state, either or both 1 and 2, state number 1 and 2, then eventually we are sure to leave the transient state and end up in one of the absorbing state. Is that correct? Because here 3 and 4 are the absorbing state. Once you get in, you can never ever leave that state. So 3 and 4 are the absorbing state. Does that make sense? Okay, so keep in mind this. For any absorbing Markov chain, if we begin in a transient state, so in this case, either 1 or 2, then eventually we can make sure that we can leave the transient state and end up in one of the absorbing state. Because this matrix tells that, right? These are 0, okay? Which means you will leave state 1 and 2 eventually, and then end up with either 3 or 4. 3 and 4 are absorbing state. Does that make sense? So using this concept of the absorbing Markov chain, we can answer these 2 questions. Okay? So the first one, if the chain begins in a given transient state before we reach an absorbing state, what is the expected number of times that each state will be entered? In other words, starting from a transient state, how many periods do we expect to spend in the given transient state before absorption takes place? Another question is, starting from a transient state, what is the probability that you end up in each absorbing state? And we use a special method that is called absorption analysis for the analysis of absorbing chain. Okay? So in this case, we consider a Markov chain with n different states. And then R, out of n states, are absorbing states. And S, which is n minus R, states are transient states. Okay? Then we could make a matrix partition. So we could make a partition the transient probability matrix P, like this. Okay? We can divide into 4 different portions. And if states I and j both be transient, then we define E sub ij is the expected number of visits to state j, given that the system begins in state I. And it has been proven that matrix E, whose elements are E sub ij, can be obtained by this formula. Okay? And actually, if you look at our text, that provides this formula as well. Okay? Okay? Just ago, I mentioned that using the concept of the absorbing Markov chain, we can answer this question. Starting from a transient state, we want to know how many periods we expect to spend in a given transient state before absorption takes place. Okay? The answer for this question would be E, which can be obtained by using this formula. And if state I be transient and state j absorbing, then we define A sub ij is the probability that the system enters the absorbing state j at some future time, given that it is initially in transient state I. And the absorption probability matrix A, whose elements are A sub ij, can be obtained by this formula. And A sub ij can be obtained by sum over n equal to 1 to plus infinite f sub ij, nth power matrix. Okay? Also, we can answer this question using the matrix A, which is from this. Okay? So starting from a transient state, there is a probability that you end up in each absorbing state. Okay? Now, using this example, let's compute both E matrix and A matrix. Okay? So using this, we are going to obtain E and A matrix. So first, what you need is partition the given transition matrix like this way, right? So this portion becomes the identity matrix. This part becomes zero matrix, right? And then which of these parts becomes Q? This part becomes Q. That is from transient to transient. And then other part becomes R matrix. So first, you need to obtain E matrix. What is E? There is I minus Q, and then you need to take inverse. So what is this? One, 1, 0, 0 minus Q, which is 0.2, 0.5, 0.1, 0.4. Is that right? What is this? That's going to be 0.8, negative 0.5, negative 0.1, and then 0.6. And then you need to take inverse. How'd you get inverse matrix for 2 by 2 matrix? Do you guys remember this? If A is given as A, B, C, D, how'd you get A inverse matrix? The A inverse matrix is going to be, let me, this way, A inverse matrix. 1 over AD minus BC, and then DA minus B minus C. Is that right? So put this number. Then it's going to be 1 over AD, which is 0.8 times 0.6. 0.48 minus, what is BC? Negative 0.5 times negative 0.1, which is 0.05. Is that right? Okay. Sorry, let me rewrite down. It looks really ugly. So this is going to be 1 over 0.48 minus 0.05, right? And then D goes here, 0.6. A goes down here, 0.8. And then put negative sign. So it becomes 0.5, 0.1. Okay? So anybody give me this number? Obviously, this part is 0.43, right? This part is 0.43. Over 0.43. So this is going to be E matrix. Okay, so in this case, I got some value. So let me delete this portion. So what I got here is It's 1.39 53 49. Here 1.162791, and then down here I have 0.232558, and then 1.860465. Okay, so that is my E matrix. Okay, now we are ready to get the A matrix. How to get A matrix? Is E times R, right? So we're going to use this value. This is E matrix, right? E goes here. What is R matrix? R matrix is here. We already identified, right? So this is 2 by 2 matrix times 2 by 2 matrix. So A matrix has to be 2 by 2 matrix as well. Okay? Why don't you compute this if you have a calculator? Actually, we already got this value. Where? You remember this screen? This is actually a matrix. Okay? You remember? We still can use Chapman-Kolmogorov equation to get the nth power matrix, right? So this is actually a matrix, but you can double check it. So obviously, I could say the limiting distribution for an absorbing Markov chain is really depends on the initial state of the process, okay? Does that make sense? Okay. So if you start from state number 1, then the long-run behavior will be different. Then you start from state number 2, right? These values are different each other, and these values are different from this. Does that make sense to everyone? Okay. Okay, so I'm going to stop here for today, and then probably for the next maybe 2 or 3 hours, we're going to devote a little bit more about this absorption analysis. And then I'm going to give you a couple different in-class exercise problems as well. Okay? So that's what you are going to do for the next couple hours. So if you do have a chance, then please read the reading material that I posted on the Canvas system. Okay? And let me know if you have any questions. Okay? Okay, thank you very much. I will see you next time.